Guys, thank you very much for attending. My name is Yuri Reznik. I run a research team at Brightcove, and the topic today will be actually quite research. I will use some formulas. I have to give some warnings ahead of time. Don't be scared. But I'll try to interleave it with some more casual words, so hopefully it will be understandable at multiple levels. And the topic is on ABR streaming and CDN performance. And it works good. So before I jump into substance, let me just review a few things from history. Just try to refresh our memories on how we even arrived with streaming concept as such, and why things been designed the way they were designed. And first thing to note is that streaming was actually not the first way media was delivered over IP. Video phones were there decades before. And actually things like H.324, H.323 stacks existed at about the same time when people started playing this concept of one-way streaming, and there were guys like VideoNet and others who were trying to use H.263, H.324 one-way, and it actually didn't work well. And there were reasons for this. Those were low latency protocols, and if you try to do streaming over 28K modems or 56K modems at that time, that latency was a very precious luxury that you could take and accumulate bits and use it for retransmissions and fix your errors and achieve better quality as a result. So first successful systems, they were all UDP-based stacks. They used H.263 derivative video codecs. Speech codecs were used mostly for audio, and the names are here: Real Audio, Real Video. I actually used to work at Real Networks at that time, so those were my babies. Vivo Active, it was a company of Bernd Giraud, Stefan Eriksson. VXstream, that was acquired by Microsoft. Of course, Microsoft themselves with NetShow as their first entrance in this area. Of course, it was done over UDP. Things were much more challenging at that time. 28K modems, as I said, was the reality. And try to send video to such connections. Then came adaptive bitrate system. So ABR system didn't came with Dash, it didn't came with HLS, it didn't came with Move networks, as many people believe. It actually came over a decade earlier. It was invented in 1998. And first streaming system of this kind was actually Real System G2. The adaptation algorithm was called SureStream. And as I show on this diagram, it's a picture of real producer with kind of selection of target audiences, where you could click 28K, 56K, like single SDN, dual SDN, and so on. So this was the means by which encoding profiles were created back in 1998. And it worked. Of course, it was designed differently. It used the UDP. It was patented. I'm embarrassed to say that I was one of the co-author of this system. But later, actually, what I discovered is that what was invented was novel in a way how multi-rate encoding was used. We encoded video and audio at multiple streams, and then we were dynamically selecting them. But the sheer fact that video and audio could be encoded in multiple streams, it was known earlier. In fact, in wireless telephony, there already existed several so-called multi-rate speech codecs. It all goes to half-rate GSM codec and later AMR family, and as well as in 3GPP2 there was VMR and ABR C-type codecs that were designed to operate at multiple bit rates, and systems were subsequently designed to adaptively switch between those rates. So what was done for streaming was novel in a sense that we did the switching after encodings was done, but the sheer concept that you could encode at multiple bit rates and switch dynamically, it was known before. And of course, why would you do the switching? Well, you do switching mostly to accommodate for changing conditions in network. If you stream over the network and all of a sudden there is a congestion somewhere, you can't maintain continuous playback. You need to do something about it. You could switch to lower bitrate stream. Hopefully that will give you enough of bits and you still have bits in your buffer such that you can continuously play some content, maybe not at the same level of quality, but at least continuously. So that was the underlying idea. And in the original system, the entity that was doing adaptation was actually a streaming server. It was selecting those streams. It was receiving information from the client, telling it which bandwidth is observed on the client end. And the reason it was that bandwidth detection was estimation was done at client was actually latency. Initially, we tried to do it on the server side, kind of trying to look at the retransmission requests that were coming back to us. But since all those things were coming over UDPs, there were round-trip delays, and it was just faster to do it on client. So that's how it went, mostly to client. But what also is important about this system is that past server, everything that goes over the network is a single stream. You decide which stream you send. You don't abuse network anywhere else with anything else. You send single streams that the client needs, and that was the beauty of it. That's how it was intended to be used. But it wasn't scalable. That's really what, and there were some other, of course, painful things about it. For example, it was UDP, your packets were lost, so you need to deal with error concealment. It was a pain in the neck to handle all those things. But the weakest point was actually server. It was okay to stream, say, 1,000 events on a single piece of hardware, but if you needed 1,000 streams, but if you needed 10,000, 100,000, well, it was challenging. So back in early 2000s, we started building proxy servers, content networks for UDP-based streaming, but it never really was well designed and as simple and elegant as later solutions that came after this, which was HTTP-based streaming. And of course, the credit for this goes first to Move Networks back in 2007. That's the first company that came out with concepts, and Apple did HLS. And if we look at this system, it looks similar to what I was describing before. The streaming client does estimation of what bandwidth is available. It decides which segment to pick. So the difference is that things are encoded in segments. But the biggest difference is that there is now a CDN here. There is origin server, of course, which is now a typical HTTP server. It doesn't do anything intelligent. But then it's connected to CDN, and CDN does the scaling. And what CDN does as part of its scaling, of course, it operates a plurality of edge caches, and each edge cache looks at the content. If it has content locally, it streams it right away. If it not, it asks it to be propagated to it from origin server in the worst case. So that's the basic concept of HTTP streaming. It simplified the problem of scaling because CDNs could be used, and CDNs were designed to do this. But there are some things that came with this, and I'll talk about this later. So it works very well when you need to scale delivery for content that is popular. Why? Because if it's popular, it's going to stay in cache. If it's not popular, it's not going to stay in cache, and you're going to actually go all the way back to your origin and pull it. The only difference will be is that you're going to pay not only for the bandwidth that you deliver through CDN, you also will pay for MIDGRESS to get it from it. So for popular content, it's best things creation. For non-popular content, it also helps. Why? Because CDNs usually have better backbones and can propagate content faster across different continents, for example. But technically, it's not as wonderful and simple as in case where the content simply sits in cache. And now let's look at this picture again, and let's try to see what is happening here. Basically, if we would be streaming just single stream, we encoded it at 1 bit rate and we're pushing all the way through CDN, it would be wonderful. CDN, if content is popular, CDN will cache it, will send it further. But we are not sending single stream. We're actually sending a whole bunch of them. Why? Because different clients, different devices will have different constraints. Some will be able to pull 1080p, somebody will stack at 360p, some will be stuck at 720p. And they will all be competing for same cache storage at the edge of the CDN for this content to be present there to get it fast. If it's not there, it will go all the way back to the origin. So that's where I see the disconnect between the original concept and what is happening with CDN. And of course, what happened with streaming recently, it actually got abused. So the concept of HTTP streaming got abused in the sense that not only we have multiple encodings now, we also have multiple formats. People package things in Dash in MP4 files, they package them in HLS, and in HLS several versions of it. There is also a variety of CDNs, I'm sorry, not CDNs, DRMs. For some legacy devices, you still need to use smooth. Sometimes you still need to do progressive, but that's a whole separate story, right? And again, that creates extra space of different formats that are hitting CDN cache and basically killing performance of the system. And last thing is actually things getting only merrier with new codecs. Because why? Because there is MPEG saying that, hey, we have a HEVC that is more efficient, please deploy it, right? Then there is Alliance for Open Media saying this is AV1, please deploy it. Well, reality of it, you cannot deploy new codec in a way such that you disconnect and terminate all streams that existed with old codec. You need to maintain everything that was before, and then you add a new codec on the top of it. Where it goes? It goes to CDN edge cache, and those new formats, again, fighting between each other for whoever is going to survive there. So that's where I see fundamental disconnect between the model and what we actually have with CDNs in terms of performance. So effectively, ABR streaming says more is better. CDN says less is better. So we need to find something in between, maybe. So now there is going to be some mathematics. I warned you about this before, but it's actually fairly simple. And
there's more pizza.
so let's try to figure out what's going to get cached in CDN. And let's consider, for example, that we have just a set of items. I call them SX, just items. It could be segments, it could be video items, doesn't matter. From mathematical standpoint, it's just elements of a set. And we have some popularity model that associated with this. This is actually a classical Zeta distribution, which is, again, it's a discrete variety of so-called pair 2 distribution, which is very commonly used for measuring popularity of content in a variety of natural settings. For example, distribution of words in English letter is a well-known example of using it. Distribution of popularity of clips on video clips on YouTube. There was a paper that said that that model fits very well. And just following the tradition, let's assume that that model is good enough. And by the way, it has a parameter, which is a parameter alpha that allows us to tune it to fit actual experimental data. So there is a degree of flexibility with this model that allows us to get to realistic data when we need to match them. Now, what's we also need to assume what is the capacity of the CDN cache. Well, let's assume that the cache can hold C items. And if cache designed ideally, what those C items will be? This will be C most frequently used items out of that set. So we basically take like X most popular items, they have highest probability. That's what we assume cache will store. Well, if that's the case, well, we can compute probability that things not going to be in cache. And that's going to be just 1 minus sum of everything that fit in cache. And that becomes pretty simple expression where there's a harmonic, generalized harmonic number, but it actually has a symptotic expansion, which is even simpler, which is basically says that it's a capacity. So the probability of miss is going to be proportional to, inverse proportional to capacity of this cache with certain power factor divided by function of the parameter of distribution. Very simple model. It's intuitive. We can work with it. And what we can do with it next? Well, now let's see what's going to happen if we have two versions of same content. It's the same cache, same capacity C, but instead of one set of items X, right, as X, I have two sets. One is S subindex 1 and the other S subindex 2. Well, what I also need to know is what is the relative usage probabilities between them. For example, one version is used in 25% cases and the other used in 75% cases. So let's denote this by P, P1, P2. And let's see what's going to happen. Well, if we know the usage probabilities, we know popularity probabilities of content by itself, then the full probabilities in terms of what is relevant to CDN will be products. And then if we look at the top a few items of what's going to stay in cache, what I really need to do is I need to sort those products of probabilities in order of their decay. And what I discover, well, assuming that P1 is greater than P2, is that that will form an interleaved pattern. So I will have first coming items of most popular, most used content. Then I will have first element of second type. Then again, for a continuous chain of from first type. Then again, second. So there will be interleaved sequence of those items where the items, the version that has higher usage probabilities will be present more prominently. That's what it really means. And if I observe this fact that there is this type of presence, then I could express what? I could express probability of cache miss in case of second. In case of two formats, it becomes this expression. It's a very simple math, and I can compare with first one. And how I compare it, I will look at the ratio of them. And if I look at the ratio of these two things, what's going to happen? The final formula that I obtain is no longer dependent on C, which is capacity of the cache. So what I discovered is that, you know, if you do some asymptotic assumptions and you look at the ratio, relative ratio of cache miss probabilities in case of single format versus two formats, then it converges to something stable that is no longer related to the actual cache size. And if that's the case, then for any reasonably large CDN, what I could say is that the ratio of cache miss probabilities will be described by this C. I can plot it, and what it shows that basically if both formats are equally probable, we stay in the middle, then the impact on cache miss will be the most significant. So if you try to push two formats over CDN and one is not used at all, this is wonderful. It's not gonna mess with the other contents, it's gonna stay there. But if you're gonna push two formats and they are both equally equal, that's where they start fighting with each other. That's where you're gonna have this very significant impact on the cache miss probability. And basically the answer here is don't do this in practice. If you want to have high CDN performance, try to push something that has as asymmetric distribution as possible. That's, yes, please.
Say that again. You're not saying don't use multiple formats, you're saying use unpopular ones?
Basically do this, figure out which format is most popular and route as many players to use just that format. and make the other formats as least probable as possible. If you have one format that is dominant in terms of usage probabilities, this is good for CDN. That means that that format is more likely going to be cached. That means more likely more players will be able to use it and more customers will be happy with it. So yes, please.
Would you explore taking this to inversions of the same content?
This could be done for arbitrary number of, so it's a similar extension. It becomes a sum of, what you see here is actually LP norm of the usage probabilities. So for n, it becomes a LP norm for n of them. So that's a very simple recipe we arrived at by just doing very basic mathematical experiment. And now let's take a look at some examples of practical scenarios where we could immediately try to apply it. And one wonderful situation will be when to deploy HEVC. It's very pressing for some question in practice, and so let's assume. So let's think that R is the rate of H.264, delta is the rate savings of HEVC. Let's assume it's somewhere between 1/4 to 1/2. Of course, standards committee says that it is 1/2 and even more. People in practical community say that it's more 1/4. Let's think it's somewhere in between. P percentage of devices that can play HEVC. And alpha is the shape of content popularity distributions that we discussed before. Then, using those things and also things that we've derived before, we can express a few things. We could say what would be the total amount of storage that is required for storing both HEVC and H.264 streams, right? What would be the average bandwidth that is used? And this is very easy because we have percentage of devices using HEVC, so it becomes a just blended average using that pi as a percentage. But then what would be CDN cache miss probability? That's where that formula comes in. And that's the expression that is essentially the most non-trivial in this exercise. And now let's take a look what would be happening with CDN cache miss probability if we just have different rate savings of HEVC, which is delta, and different reach probability, which is pi. So what we see is that there is a region, which is this triangle showing, where HEVC will actually reduce the cache miss probability. But to hit that region, you need to have, if you're saving 50%, you need about 82% of devices supporting HEVC to be in that region. That's what this mathematics says. That's just cache miss probability. But you will say that cache miss probability is not a true indicator of total costs, right? It just indicates at which point deployment of HEVC will be breaking even if you don't have any caching at all, if you're streaming extremely non-popular content. But if you're streaming popular, it's probably different story. So let's take a look at overall traffic costs. So the overall traffic cost is going to be this. It's going to be traffic that cost we're paying at edge for traffic going from edge plus cost we're paying for MIDGRESS. It becomes a blend of those two. And plugging in the formulas that we've seen before, we can show this. If we do have a situation where the MIDGRESS traffic is much more expensive, which is the case with many CDNs, then the ratio of total cost of sending H.264 plus HEVC over HEVC boils down to this expression. So this Xi, which was our fraction indicating the change in cache miss, is just one factor. The other factor is 1 minus P delta. And if you plug this, it actually becomes a more favorable for HEVC because the area where we start seeing gains is much broader, and even if rates is savings at 25%, hitting about 1/3 of devices becomes sufficient, such that if you look at overall CDN costs, you will start breaking even. So that's basically the mathematics that describes the trade-offs in this case. Another case, and the last case that I will consider, it's another popular topic of the day, is when it makes sense to deploy CMAF. It's a new standard. There is much hope that it will drive conversions of both Dash and HLS in industry to a single format, which of course will help CDNs to achieve high performance. But the problem is that if you try to deploy CMAF today, the way you can deploy it will be additional. You will still need to support devices that can only play HLS as HLS devices, and so it gives them an option to load HLS devices that can play Dash devices, play Dash in whichever flavor they support, and then CMAF comes third. So from that consideration, what we really have mathematically here is a comparison of 3-format systems versus 2-format systems. And you would think that probably 3-format systems will never be better than 2-format systems. You're adding an extra format, how in the universe it may help CDN performance? Well, if you remember, when I did my initial exercises, I showed that if you have a single format that becomes dominant, that actually helps. So what I'll show in a few last 2 pages is that if we have sufficient number of devices that will be able to support CMAF, that becomes the point where deploying it will actually start saving money right away, even considering that you still need to support HLS and Dash devices by themselves. So these are cache miss probabilities in both cases, in cases of 2-system and 3-format systems. Actually, I think I screwed up. This shouldn't be here. But that's all right. So the first one is just takes 2. The second is row, where rows are usage probabilities in case of 3 formats. Then let's also assume that when CMAF is deployed, there is a kappa, this funny letter, that represents a percentage of both HLS and Dash devices that will be able to switch and decode CMAF right away. So a kappa is basically percentage of devices, of existing devices that will be able to take CMAF. And then what will be probability of CMAF is basically it will be kappa times P1 plus pi2. Then the residual probability of devices that support, for example, only HLS is going to be 1 minus kappa times pi1, and residual number of devices supporting Dash will be 1 minus kappa pi2. So that's how it works. And then we could just compare cache miss probabilities in case of 2-system versus 3-system, where in case of 3-system we use this raw probabilities that are shown here. By doing a little bit algebra, it becomes equivalent to basically looking at this inequality where the parameters are now kappa, alpha, and pi. And basically this is what it boils down to. So kappa here means a percentage of devices that can play CMAF. Pi is a trade-off between existing HLS versus Dash devices. And again, the 0 is a plane where those probabilities will be the same. So if it goes down, it means that CMAF is actually allows us to reduce costs. It allows us to reduce cache miss probabilities. And so that region becomes well characterized in this case. And doing some plugging of ballpark numbers, such as 1.16 for the decay of the popularity distributions, and assuming that, for example, 75% percent of devices use HLS versus 25 use dash, we arrive at a wonderful factor deployment for CMAF, which is 0.084 that is needed to make that standard successful. Few mathematical exercises with some consequences for some known problems. So,
Yuri, sorry to interrupt. So if you go back, so with kappa calculated to be 0.84,
yes,
is the interpretation that 84% of devices
should support CMAF, should be CMAF capable for it to hit, to have same cache miss probability as you have now with two formats. And this might sound like a high number, but if you consider the fact that you already have two formats and you are now adding third on the top, that's where it really becomes much more harder barrier to go over. So that's the minimum density you need to hit to make it worthwhile economically. Conclusions, simple model proposed, several examples given, but it's actually, I think, it's just the beginning. If you remember, when I started talk, I was talking about how ABR streaming was designed to begin with and what the objectives were. And in my view, the addition of CDN happened in somewhat ad hoc manner without due thinking about how this should be done optimally. And perhaps if we think deeper about it, if we use models and understanding of what actually will be cached, what will not be cached, what the impact of that will be on network bandwidth distributions, maybe we can design systems that works a lot better than what we have today. Thank you very much.
Anyone have any questions that they want to ask? Are you going to stick around?
Yeah.
Okay.
So you know.
How far are we from the 0.84?
My sense is that first, most Apple devices already support it. And some TV players, some smart TVs also can play it back. So it really depends on operator. It really depends who you're talking to. If you're talking to somebody who is streaming predominantly to Apple devices today, maybe he is already crossing this line. Keep in mind that those distributions, they are not absolute industry-wide. They're always specific to the context of each particular customer. So overall, if you think all platforms together, of course, we are not quite there yet. So what I know is that CMAF, support for CMAF was added in some late builds of Chrome, but how stable it is, I do not know yet. But once that is stable, that of course will cover a significant portion of desktops. And of course, Android will be the last thing that at this point I just don't know anything about. So.
MPEG is also looking at relaxing restrictions on what CMAF is defined by, such that the ICP web segments per dash qualify as CMAF.
Yeah.
So that would automatically enable most dash clients to make.
So I honestly think that CMAF is the best thing in a while that is happening now, and especially considering everything I was saying before, that basically the less is better from CDN perspective. So driving that commonality is, of course, a big deal. The question is how to get there, and how to get there without breaking everything that exists already. That's where the challenges are. That's where the initial deployments will be facing trade-offs, and you need to design systems that is more complex than ideal single format system in the end.